Hello, welcome to Chapter 6 of Gilgit Community College Math 100. This is a chapter on measurement. We'll start with the American units. The American system is one of the main systems of measurement, and it includes all the things that you know in your day-to-day life, right? It says American system. It's actually called the imperial system, but you probably know it as the American system because we're one of like 2 or 3 countries in the world that still uses it. It says it's one of the main systems of measurement. That's a funny phrase to me because, again, the vast majority of the world does not use the imperial system, as shown here. So, debatable if it's really a main system of measurement. But these are the ones that we as Americans are very familiar with. Length and feet, inches, yards, miles, what have you. Weight in ounces, pounds, and tons with one O and no E. So, volume and ounces, cups, pints, going on to gallons, etc., like that. It says time here in seconds, minutes, hours, days, and weeks. That's not an imperial system of measurement. Time is time no matter what system you're using. So I argue it shouldn't be here, but Pearson's is our corporate overlords. We do whatever they say. Yep, there's your quart and gallon. So yeah, these should all be very familiar. You probably know a lot of these off the top of your head. 12 inches in a foot, 16 ounces in a pound, 2 cups in a pint, 2 pints in a quart. You probably know a lot of these stuff already. We'll go into how to convert them later on, which is the true point of this chapter. But just to make it abundantly clear, when I say American or imperial system, this is what we're referring to. So, this is, in my opinion, one of the most important concepts in elementary or sort of fundamental mathematics. The concept of unit conversion. A lot of questions that you run into, not only in your day-to-day life, but also in your math classes and then your classes at a university level, essentially boil down to conversions. The method shown here at the bottom, you may know it as a times bar. You may have heard that before. But this is the basic equation for converting stuff. Essentially, the idea behind this process is each of these equations shown here is actually also a fraction, right? That fraction being the form of 12 inches per 1 foot or 1 foot per 12 inches. This, and this, these all represent the exact same concept. All of these 3 ways of writing the sentence are identical. And that's very important to understand. Because, right, as we've talked about in previous chapters, what is a fraction? Well, that's something divided by something else. What is a ratio? That's just a fraction. How do you say the stuff in English? That this bar here means per, right? Each way you can write a equivalency can be written as a fraction. And since they can be written as fractions, they can also be used in math equations. Because, of course, as we talk about, right, fractions are used in math equations. You don't use percentages in math equations. You use the decimal or the fraction equivalent. Practically, what that means is since we know that 1 foot equals 12 inches, and we can write it out either this way or this way, we can use the concept of canceling to help us solve problems. We're all aware, let's say, 12 times 2 over 3 times 12. Well, these 12s can cancel to give us 2/3, right? That's a concept we've already established in previous chapters. And the idea is if you're doing the same thing to both sides, you're not doing anything. I've covered that a lot in this class. That idea we've only really established with numbers to this point, but now that we add units to the conversation, that same philosophy works with units. This is why I've also said it's always good to write your units in all your work, because eventually it's going to come into something very important. In this example here, can I back you up at all? No, it's only crossed out. Okay. In this example here, we notice convert 150 inches to feet. Okay. Well, if you're just going to think about the wording, think about how to solve this in your head, you know that there are 12 inches in a foot, right? But is this question going to be 150 times 12? Or is it going to be 150 divided by 12? Well, it's supposed to be a 12. Because we both know, right, those are very different answers. 150 times 12 divided by 12 is very different. Which one of these two options is the correct course? The way to answer that question, if you don't know off the top of your head, the way to answer that question is to write out the equation and solve for it. If you write out the equation and you use the units while you're writing out the equation, you can find this to be a lot easier. So as said here, you start off by writing 150 inches. You write inches there, and you also remember that technically every number is a fraction with that number over 1, right? 150 inches, as shown here, is the equivalent of 150 inches over 1. That 1, of course, at the bottom being unitless. Cool. Since this is a fraction, we can then say, okay, my question is in inches. I want my answer to be in feet. A common way of going about this is to write out what you know, 150 inches, do a multiplication sign and a division sign, times bar, right? And then have equals some amount of feet. When you write out the skeleton of the equation in this manner, this tells you what your end goal needs to be. Your end goal needs to have feet. And notice there's no division over that feet, right? There's no, we'll try to write it in red here. This doesn't exist above the feet. There's nothing below here either. Since neither of those two exist, that tells us our answer needs to just have feet in the numerator and nothing in the denominator. Cool. Now we know we have inches in the numerator. We need to end with feet in the numerator. We need to find, let me go back here real quick. We need to go back and we need to find an equation, this equals that has, see if we have one that has both inches and feet in it. In this example, this guy here has both inches and feet in it. Sweet. So let's take this idea of 12 inches to a foot. What am I at here? 12 inches equals 1 foot. And I can write this equation in 2 ways. And again, I'm going to go over this in a lot of detail. If you get confused on this, you need to go over it in this exact detail. That's the best way for you not to get it wrong, right? We always have a problem when we do math of trying to get to the answer, get to the end as fast as we can, and we end up making a mistake along the way. So I have this basic equation set out. The 2 ways I can write that as a fraction are 12 inches over 1 foot, or 1 foot over 12 inches. Notice I wrote my units along with my numbers, and I kept the unit and the number combined. The inches was next to the foot here. So actually, do I have a, just a second, there we go. The inches was next to the 12 here. So the inch is next to the 12 here, and the inch is next to the 12 here. I kept my units and my numbers together. That's important. So I have these 2 options for fractions. I need to figure out which of those 2 options flows best in this equation I have down here. Well, I know I need foot in the top. Foot is my numerator, so which of these 2 has foot as the numerator? this guy does, right? It's highlighted in purple. Yay, there we go. Look at all those colors I got. It's so fun. That equation gives me foot in the numerator, which is what my answer needs to be. Sweet. So I can write that in this part of the equation. Now I can look at the equation. I can say this is what happens down here. I can look at the equation. I can say, okay, this is multiplication of fractions, which means we multiply straight across, right? Since we multiply straight across, this guy, what does spotlight do? Oh, hey, look at that. That's fun. This guy here is the equivalent of saying 150 inches times 1 foot as the numerator, and then 1 times 12 inches in the denominator. Now we look at this overall fraction, this equation fraction conglomerate we have here. We can say, okay, do I have anything I can easily cancel? Well, in this case, I do, right? I have inches. I have inches in the top here, and I have inches in the bottom here. I have the same thing on the top and the bottom. That means they cancel. Pow, bang, boom, blow them up, right? We don't need the fact that inches exist in this equation because they're on the top and the bottom. They cancel, they're redundant, they blow up. So we can blow up the inches, and what that leaves us with is an equation that only has one unit. There's still math involved here. There's still math involved, but there's only one unit, and it's feet, and it's in the numerator, which is exactly, right, what we wanted our answer to be in. So my math equation is set up now. All I need to do is do my math. Well, in that case, okay, these ones can cancel. They're pointless for multiple reasons, giving us the equation as shown down below here of 150 divided by 12. Pull out your calculator, that on 12.5 feet. That is how many feet 150 inches is. Is that a lot of work to get to the solution? I could see that argument. But until you are really good at setting this up, do as much work as needed. Please do the work. If you get to the point where you don't need to do the work because you've got this stuff well situated, you know how to use these fractions in a, you know how to use these fractions in a useful way, cool, you can skip a lot of these steps. But until you know how to build these skeletons of equations here, it's super, super important that you actually, okay, well, I know that 1 foot equals 12 inches. My fraction options are this. I hate writing with a mouse. Or this. Which one works? You got to go through all those steps if you're not going to make mistakes. And we don't want to make mistakes, right? So, converting ounces to pounds. Again, I'm sick. I'm sorry about that. It sounds gross, I know, but I'm sick. I can't do anything about it. So, if you're watching this on YouTube, I'm going to suggest you pause the video here. Try to show the work to get this answer correct. In this live stream, I'm going to just run through it. However, I encourage you to work through it before I get to the end to make sure that your work looks like mine. Meaning, all this time I'm spending talking, I hope that you are writing stuff down and you are trying to answer these questions. Convert this to this. Well, okay. What do I need to solve this problem? It looks like my question is in the form of 144 ounces. Let's just say O for ounces. I can't remember the shorthand version of it. And that's going to equal some amount of pounds. O-N maybe? Ounces? I can't. Whatever. Some amount of ounces equals some amount of pounds. Ounces and pounds are different units, so I need to convert the unit with at least one times bar, at least one unit conversion. So I need to know, is there a equivalency of ounces and pounds. Can I just go straight from ounces to pounds? And to find that out, we go back here. We say, all right, is there a ounces to pound conversion? Hey, look at that. There are 16 ounces and 1 pound. Sweet. Let's use that. And let's say 16 ounces. Oh, God, that 6 is horrible. Equals 1 pound. Okay. So my options for fractions are 16 ounce. Oh, what is the shorthand for ounce? Anyone know? You can type in the chat or tell me. I can't remember.
It's OZ.
Oh, Z. Thank you.
You're
I'm
welcome.
embarrassed I forgot that. Jeez. So,
You had half of it right.
I suppose 16 ounce per pound, or we have 1 pound per 16 ounce. Those are my 2 fraction options. Cool. So, let me draw this a little prettier if I can. Oh, there we go. That's not too bad. So I have these 2 options here. I have these 2 options to put into this fraction spot. Which one do I want to choose? Well, let me get my drawing marker back here. I know that my answer needs to have pounds in the numerator. So lucky for me, this guy has pounds in the numerator. Cool. So the question, so I can drop the n here. 1 pound, 16 ounce. Let me clean this up a little bit. Oops. Eraser. There we go. Now I can look at my equation. I can say, okay, I have pounds as my numerator, and I have ounces in the numerator and ounces in the denominator. Those 2 cancel, meaning my math is 144 divided by 16. Right? Notice here, the ounces cancel, leaving pound in the numerator, which is what we wanted. And then this math, you can just do with the calculator or however you want to do it. Pretty straightforward, not too bad, I hope. Now, let's, again, pause the video if you watch YouTube, or start working on this question before I get to it. Convert 18 hours into seconds. What do we do? What do we need here? Well, I'm going to suggest start by writing out the skeleton of the equation. I know I'm given 18 hours, so I write that. I know my answer needs to be in seconds, so I write that. These are different units, so I'm going to have to do a unit conversion, at least 1 unit conversion between them. All right. Now, do I know the seconds to hours comparison? Well, you can either look it up, or you can go back to that handy dandy chart we have back here. Look at time. I need hours to seconds. I have hours to minutes. I have minutes to seconds. Okay, that's workable. I know there are. I don't have a hour. If you know how many hours, seconds on an hour, you can skip this step. I'm going to go with it long form, right? So we know, I'm going to rewrite my equation up here just for consistency. Oops. Change that a bit. There we go. There we go. So I know that there are 60 seconds in 1 minute. I know there are 60 minutes in 1 hour. Notice neither of those convert straight hours to seconds. But if I write these as fractions, I can organize the fractions in such a way that my equation ends up turning hours into seconds. By that I mean, both of these options, again, I'm going to be super rigorous here, both of these options have 2 fractional formats, right? This top guy has 60 seconds per minute and it has, it's supposed to be an or, 1 minute per 60 seconds. Okay. And then the bottom guy here has 60 minutes per hour and, 1 hour per 60 minutes. Those are my 4 fractions. They all contain something I need. Hours and seconds are what I need. Those 4 fractions all contain them, so it's kind of a pain to look at. So I know my answer has to have seconds in the numerator, right? Let's go with, I don't want pink. There we go. My answer has seconds in the numerator. Do I have any of these fractions of seconds in the numerator? Yes, I have seconds in the numerator right here, right? So that tells me that this guy is part of my equation. Cool. So let's start writing it. Rewrite it down here. 18 hours times bar equals some number of seconds. I'm going to technically do this in an incorrect fashion to start out with. Then I'll explain my process as I go. I know my answer is in seconds to minutes. So I could write 60 seconds over 1 minute here. Because I know I need that, right? Now I have hours and seconds in the numerator, and I have minutes in the denominator. That's weird, right? Because this is going to be just the pure units here is going to be hours times seconds over minutes. I want my answer to just be seconds. So what do I need here, right? What I need is I need a way to get rid of the hours and get rid of the minutes. How do I do that? Well, if hours is in the numerator, I get rid of it by having hours in the denominator. Right? So what I need, there we go, is something with hours in the denominator, and then I also need something with minutes in the numerator. That's how I can get rid of these 2 guys I don't want. Cool. All right, there we go. And, oh no. Do I have an equation with minutes on the top and hours on the bottom? Hey, look at that. I do. Minutes on the top, hours on the bottom. Fantastic, right? We can use that. So let's get rid of all this stuff here. What that means is I can add that to my big old equation. I could throw 60 minutes up here, and I can say 1 hour down here. Now my equation has hours in the numerator, hours in the denominator, minutes in the denominator, minutes in the numerators, and seconds in the numerator, which ties into my answer. That is my math. So my units all blow up, and my math looks like 18 times 60 times 60. I said when I started this, which equals 64,800. I said at the beginning, I did this sort of backwards. The way I did it backwards is I placed the seconds to minutes guy, I placed this guy in the second row. Since I knew seconds was in my numerator, I really should have placed him at the end, meaning my equation should have looked like this one down here at the bottom. Over 1 minute equals. My equation should have looked like this, because this seconds turns into, let me just spotlight. This seconds turns into this seconds. So this tells me if I write it this way, I know this is going to be the end of my equation, but hours and minutes don't cancel, so something needs to go in the center. However you choose to do, it's up to you. As long as you draw out your skeleton and you follow the course correctly. See? In this example here, right, they put second minute conversion back here, and then they leave an open spot here to convert that over. I know I'm being exacting about this. I think it's important. This is something that is super useful in basically every step of your math life. Example 3. A painter has 26 quarts of paint. How many gallons of paint does he have? Okay. I don't know that off the top of my head, but I can figure it out by conversion. So what this question, the skeleton of the question says I'm given 26 quarts, and I want to know gallons. That's the very basis of the question. Quarts and gallons are not the same unit, so I need at least one conversion, maybe more. Now I need to know, do I have a conversion from quarts to gallons? To know that, I look it up, right? Or in this case, we're back to the chart. And I notice down here, I have 4 quarts and 1 gallon. Sweet. I do have a straight conversion, so I can 4 quarts equals 1 gallon. Cool. I'm going to skip a step here and notice, hey, I have gallons in the numerator. I have quarts in the denominator, which means I need to have gallons in the numerator and quarts in the denominator. I'm going to keep this 4 with this quart, and I'm going to keep this 1 with this. Oh, I did it backwards. Hey, look at me. Keep that 4 with that quart. I'm going to keep that 1 with that gallon. So 1 gallon here, 4 quarts there. My quarts cancel, giving me my mass, which is 26 divided by 4, or 6.5 gallons. All right. I built my equation. I knew I needed to divide the numbers instead of multiply them, and I got the correct answer. Ooh, yeah, I should have adjusted that. A shipping company, again, when I'm done here, pause the video, work on, then make sure your work matches. A shipping company charges 18 cents per ounce to ship small packages. How much will it cost to ship a small package weighing 1 3/4 pounds? That's what it's supposed to say there. This is supposed to say weighing. Although it's not supposed to be capital. There we go. So, a lot going on here, right? I have weird units. I have differing amounts of weight. How do I solve this? Well, you start with what you know, and you put in what you need to change. So, I know the package weighs 1 3/4 pound. Cool. What do I need to know? I need to know how much will it cost, right? I need my answer in dollars. And I have a conversion shown here. 18 cents per ounce. All right. What does that mean? What is per, right? Per is the key word there. Per stands for division. So that is 18 cents per ounce. OZ. Look at that. I did it correctly. Cool. So I have a conversion already set up per 1 ounce, we could say. And I have a poundage note. I can start building my equation and figure out what I'm missing in this conversation. So I know this guy over here has dollars in the numerator. I have dollars in my denominator. I have dollars in my numerator for my answer. This means most likely that this fraction here needs to go at the end of my sentence. So I probably have this guy right here. I'm giving myself space here on purpose. Maybe I need it, maybe I don't. Ounce. And the question is, does ounce and pound cancel? No, they don't. So I need a pound to ounce conversion. If I can find one that does pounds on the bottom and ounce on the top, so that this pound and this pound cancel, this ounce and this ounce cancel, right? That's what we're hoping for, is to blow all these up. So I need to find out how many ounces are in a pound. Well, I can go back my chart. I could just know it. In this case, there are 16 ounces in 1 pound. Now my units have blown up and I can correctly answer the question as shown down here. 1.75 times 16 times 0.18. So there's a few different ways to look at how to read these guys, right? In this example, everything's in the numerator, so it's all multiplied. If you have things in the denominator, that means you divide them. We'll get to some examples where you have to multiply and divide as you go through the conversation, and I think it'll probably make a bit more sense at that point. But at this point, do we have any questions we want to ask? Anything that we're not quite getting? Right? This is math we know. It's just setting it up can be kind of tricky. So we hopefully can set it up correctly. That's the big thing, is the setup. I don't see any questions really. You can ask questions in the group chat if you want. You raise your hand, do whatever is necessary. If not, I'll just continue. All right, so that was the imperial system, or as they say, the American system, because reasons, I guess. Let's take a look at the metric system. I'm sure you're all familiar with the metric system in some way, shape, or form. I will say the metric system is what's used throughout the world. It's what's used in science. You get a job in science or medicine of any sort, you're going to be using the metric system. The metric system is useful because it cares about the power of 10. And as we talked in previous chapters, power of 10 is add zeros, right? 10 to the second is equal to 100, because that is a 10, and it is a 1 followed by 2 zeros, right? Power of 10 stuff. Metric system works in this exact strategy. All changes in size are just add a 0 to the number or move a decimal place around. That's all it is. Again, to remind you, each of these is different, right? 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile, 1,760 yards in a mile, 2,000 pounds to a ton, 8 ounces to a cup, 2 pints to a quart. All of these are different conversions. So you need to have every one of these conversions either memorized or written down someplace if you're going to make these adjustments in the imperial system. However, the metric system is just changing stuff by 10. Since kilo, again, I apologize for the snotty nose, I am sick. Since kilo means 1,000, a kilometer or kilometer is 1,000 meters. Since centi means 100th, right? And to remind us, 100th, right? 10th. And then 100th, I'm not going to spell that, it's expensive. 10th, 100th. Since we know centi, that was my spotlight. Since we know centi means 100th, centimeter is 100th of a meter. Decameter, deca is 10, deca is 10 meters. Deca is used more so in other parts of the world, not really used in America, but deca and deci are good things to know. I have to blow my nose here a little bit. Lord, I have to take a quick 5-second break. So, how do you convert units in the metric system? Again, metric conversions are simply a movement of the decimal place. If you have, as shown here, 1 meter of something, and you want to convert it forwards or backs, you just remember, okay, millimeter, that's thousandth of a meter, so you multiply it by thousandth. Or another way to put that is you bounce the decimal place back the correct amount. If it's useful to remember this prefix is a meanings, that works. This becomes very inherently easy as you go about it, because all it is a movement of the decimal place, right? How many 125 centimeters, how many meters is that? Well, there's 100 centimeters in a meter, so I need to move the decimal place up 2 because 100 is to the second power, right? This is math we've already covered. I'm just putting fancy words with it. There are lots and lots of metric abbreviations, but the cool thing is those abbreviations don't change given what you're measuring. If you're measuring length, use kilo, hectare, deca, deci, milli, pica, whatever you want. If you're doing weight, you do kilogram, gram, microgram. If you're doing what's that? It's volume, yeah, volume. You can do kiloliter, liter, milliliter, stuff like that. Where am I at? Go back here. There we go. The prefixes don't change depending on what you're talking about. It's just the unit, the suffix, the word used at the end of the measurement is the only thing that changes, and that suffix tells you how and what you're measuring. Meter, length. Liter, volume. Gram, weight. It's just that easy. And, in a just world, we'd all be using the electric system and have ditched the imperial system a long time ago. But America, it just is the way it is, I guess. Right? This is math we've already done. I don't feel as though I need to belabor this point very much, sadly. I guess the thing would be, since we're not super familiar with metric system, trying to picture what these things entail. A good way to kind of remember it is a meter is about a yard. So for this example here, Carlos looked at a map to find the distance from town to the state park. He wrote 20.5. Which unit did he use? Well, a meter is about a yard. So is the town about 20 yards from the state park? Does that make sense? Well, probably not, right? 1 meter is about 1 yard. Okay. Kilo means 1,000. So, and if we say a meter is a yard, 1,000 meters would be, let's say, about 1,000 yards, right? So 20,000 yards, or 1,000 yards, that's getting kind of close to a mile, right? Miles are long, 1,000 yards would be pretty long. So about 20 miles out. Kilometer is, again, you kind of talking mile at that point. Well, that could make sense. The state park, 20 miles outside of sound. That could make sense. Centi is hundredth. Tiny, right? A centimeter is the closest thing to a centimeter is, I think, like a half an inch or something like that. Centimeters equivalent, if you will, is, that was a terrible little drawing. Centimeters equivalent, if you will, is inch. What am I doing here? I am horrible at this. There we go. So, is the state park being 20 inches from the town make sense? No, right? These are rough translations. The more you use the metric system, the more you get used to it. Easier everything remains. It is, I would argue, truly a superior system in basically every fashion. The only reason why it's not superior is the fact that we're not used to it here. That's literally the only difference. So, oops. So we could do complicated math such as this here, 523 millimeters plus 47 centimeters plus 4 centimeters, and we can make that very easy math to do because 523 millimeters is simply a unit conversion. Millimeter to centimeter, as we talk back here, I gotta go blow my nose. I'm sorry. 5-second pause where I go blow my nose. All right, sorry about that. What was I? Okay. Centimeter to millimeter is hundredth to thousandth. And if we remember, hundredth is 0.01, thousandth is 0.001. That's a change of one decimal spot, right? There's 1 0 difference between those two. Translated millimeters to centimeters is the easiest moving the decimal place over 1. So when we have that seemingly difficult looking question, millimeter centimeter, well, that's a decimal place motion of 1. 523 millimeters is 52.3 centimeters. And then the math, right? Math is easy. It's just addition where you keep your decimal place in line and add it as you go down. Super simple, right? Imagine if this was inches, feet, and yards, right? That'd be a lot more converting you'd have to do. Doesn't work that way with millimeter, centimeter, what have you. There are lots of different prefixes in the metric system depending on what you're talking about, and they all follow the same basic principle. Mega is 1,000,000, giga is 1,000,000,000, micro is what's that, a millionth, I think, right? Tens, hundredths, thousandths, 10,000, 100,000, millionths. Yep, micro is a millionth. Million. There we go. Nano is a billionth, I'm going to assume. I don't want to count it. And yeah, that's how it works. Those of you in the medical field, micrometer is going to be used. Millimeter, micrometer is going to be used all the time. I guess you are astronomers, mega is used a lot in astronomy. Yeah, 32 megameters, 32 million meters. That's the equation. You don't even need to do math, really, right? That's just a decimal place movement. Other various ways we could use this is computer metrics, such as the byte. I'm not going to get into how computer memory works and, binary and stuff like that, and zeros and ones. But if you ever heard of a gigabyte, or perhaps your camera on your phone has so many megapixels to it, right? That's the exact same format, the exact same prefix idea of the metric system, where you use tera, giga, mega, kilo, what have you, to define thousand, million, billion, trillion, whatever you need it to do. If you have a not bad computer at your house, it may have a terabyte hard drive, meaning a trillion bytes of information. That's rough estimate. It's probably a bit different from that, but that's how this game is played, right? It's super, super easy. A lot less work. When we get into unit conversions more as we go, you'll see the different various ways that can be done. You can do this using the unit conversion skeleton I showed you, but it's just a movement of just one place. If someone wants me to go more deep into that for these questions, I can. I can also, if you want, hit me up in the comments or email if you want and ask for, we can go over this more in depth one-on-one if necessary. But I believe this is not something that's going to require a lot of additional work as opposed to, say, the imperial system of how many hogs heads are in a, donkey foot or whatever random words they decide to use. Volume of weight, I said this already, exact same concepts here. A liter is the same thing as a cubic centimeter or cc, and it's the way you measure volume. 1 liter is 1,000 cubic centimeters or 10 centimeters on a side. Liters, 1,000 liters, and milliliters, 1,000th of a liter. Again, not difficult stuff to figure out. A liter is a little bigger than a quart. Again, if you're in Europe and you buy milk, you buy it in the liter. You don't buy it by gallons, sorry. You buy it by liters. You don't buy a 20 ounce of Pepsi, you buy a half liter of Pepsi, right? Exact same philosophy, just a lot easier to scale with the metric system. In fact, it's a lot easier because it's the exact same thing. Yeah. Pretty straightforward. Again, if you are wondering if you have an understanding of this, please pause the video. Take a scan at this. Make sure that you get these same answers. But it's jumping around. Once you have that basic understanding of what the prefix means, it's super easy to understand. Remembering the prefix is really the hardest part. And let's be honest here, unless you use it in a day-to-day fashion, most people probably just look it up if they don't know. If I tell you a hectoliter, I don't expect you to know that's 100. Just look it up. It doesn't matter, right? Eventually you get good enough at hectoliters to know what a hectoliter is, what hecto means, 100. Only reason I know is because I teach this stuff a lot. I never use hecto in my day-to-day life because I'm a proud American. And hecto, that's crazy European talk. No offense to Europeans that might be listening to this. Right. Again, pause the video if you want to. If you watch this on YouTube, pause the video. If you got a question, you want me to go over something, please let me know in the chat or raise your hand or yell at me, however you want to do it. But again, I feel as though this is not something I need to belabor because we've covered this stuff in previous chapters, how to move decimal places. And as long as you know how many decimal places to move, you're good. Right? Gram is the unit of weight. We define gram as how much 1 cubic centimeter of water weighs. So 1 cc of water weighs 1 gram. I couldn't tell you where pound comes from. I couldn't tell you where ounce comes from. I have no idea. Grams are teeny. But they still use the same prefixes, right? I don't know how much more I have to belabor at this point. The only real difference here is they do have metric ton, which is a lot, I guess. What is metric ton? Metric ton's a million. Why don't they use megagram for that? Well, lots of places do use megagram, but metric ton's also commonly used. I believe you will see metric ton as TONNE sometimes. Possible. I've always seen that like when dealing with European stuff, but stay with me. Right, just jumping around, placing decimal points in different locations. We've dealt with this stuff already. I'm not going to belabor the point. If you have any questions, we can talk about this more in depth privately later. It's up to you. Just let me know. I don't want you to fall behind because you're nervous about talking on Zoom or something. So you can email me or message me on Moodle or Canvas or whatever. Small weight measurements, dealing with very small particles, atomic elements, units smaller than grams are used. Micrograms, nanograms, picograms. Only you're going to see this in chemistry, and then you're not really going to care about it for the vast majority of people. But yeah, these again, pico, nano, micro. These are all prefixes that are applicable to every single metric system. A picoliter exists. It's essentially pointlessly small because what you can't really call it a liquid at that point. Picometer exists. It's kind of pointlessly small. I think atoms are even bigger than picometers, but the point still remains. This is a trillionth of a gram. It's stupid small, right? And all these conversions work by moving decimal places. Have I beat this dead horse enough? Are we getting this understanding? At this point, half the class would nod their heads and roll their eyes, right? Converting between imperial or American units, make sure to salute when you say American units, and metric units can be helpful because, God forbid, we change over the metric system like the rest of the world. You know, geez, hate to have to go in kilometers per hour. Here's some conversions. Like I said, an estimation of a yard to a meter or something like that works as an estimate, but it's not necessarily accurate. See here, a kilometer is more like around half a mile than a mile, but again, c'est la vie. At the end of the day, all of these conversions, what do they look like? Well, these guys look really dang similar to what we had at the beginning of the chapter, where it was something equals something else, right? Each of these examples can be written as a fraction, therefore can be used in that skeleton of a unit conversion. 1 kilometer per 0.62 mile, right? Give it that dot. There we go. Look at that. That is that. Cool. I'm going over well-trodden ground at this point. Hey, there's standard abbreviations. We probably know all these except for ounce, apparently, because I'm terrible at this game. Standard abbreviations for all the metric prefixes. Cool story. Worth it here. You will see some metric system does have an issue where sometimes things are capitalized and sometimes they're not. In general, they're capitalized leaders. Sometimes the kilogram will be capitalized, you'll see. Sometimes it's all going to depend on what you're talking about here. The letters are different, though. You understand what's going on. So, how do we do these conversions, right? How many yards is 5 meters? Well, lucky for me, I have this nice comparison to know that a yard is about 0.914 meters, or a meter is about 1.09 yards. Okay, so let's write both those down and see if we can get the same answer either way. Spoiler warning, you can. 1 yard is equal to 0.914 meters, and 1 meter is equal to 1.09 yard. All right. Convert 5 meters to yards. Well, what do we do? 5 meters. I want my answer in yard. Oops. I want my answer in yard. I need to convert at least once. I have 2 conversions, do meter to yard. I could use either of these, right? I can either do what they did, where I multiply it by 0.109, or if I wanted to, I could put meter on top. What am I doing here? Oh, sorry. I could put, do that backwards. Meter still needs to be on bottom, but I can hold the number with the meter. There we go. Get the same work because divided by a number less than 1 increases it, right? And this is the same math. It doesn't matter which one I do from that unit conversion chart, I'm going to get the same answer regardless. If I choose the one where 1 is in the numerator or the 1 is in the denominator, the math's the same. I'm saying that because it's important to know, as long as your units work out, as long as the meters blow up and you're left with yards, I don't care what math you do because it's going to end up being the same thing. They're all just straight conversions. Convert 125 gallons to liters, right? Go back, figure out your liter to gallon ratio, choose your favorite one, make sure your units cancel, centimeters to feet. In this case, we're going to have to, this example uses a intermediary of inches to centimeters because feet and inches don't play that well. Sorry, because feet and centimeters don't play that well, but inches and centimeters, but feet and inches do. So they use a mid-step there, and it's just all about figuring out what you need, building your equation, making sure it works out. I guess to go over this for a bit more in depth, how would I write this skeleton? Well, I'd write what I know, 500 centimeters, and I'd write after an equal sign what I want to know, feet. And if I can't find a centimeter foot conversion, if I cannot find something that does this, I need to find something that has feet in the numerator over something, blah, blah, blah. And I also need to have something that has centimeter in the numerator and feet in the denominator. And if I, I'm sorry, not this, obviously. I also need to have something that's feet in the denominator and something that converts from centimeters in the numerator. In this case, they did inches, and then they did inches over. So it's all about looking at your information. It's all about figuring out what I need to do to solve the problem. Take your time, write stuff out, write out your fractions as you need to write them out. You'll get there. Works best, I believe, with practice. Example, a race car crosses the finish line at 200 miles per hour. How many feet per second is the car traveling? Interesting, right? This one's cool because our question has units in the numerator and denominator, and our answer has different units in both the numerator and the denominator. So we start out with 200 miles per hour or per 1 hour, and our answer is in feet per second. So not only does the numerator need to change, but the denominator needs to change. Again, at this point, I'm giving you a hint. Pause the video, try to solve it, make sure your work looks like what is down below. If you watch this live, start working on it while I'm going on and on about the same subject over and over again. Get yourself a head start over what I was doing. See if at the very least you can construct the skeleton of the equation. That's what we care about. Cool. What do I want to change? I want miles to change to feet. Luckily, miles and feet are both imperial, both American, salute, systems. So I need to figure out a way to convert those. Do I know how many feet are in a mile? That is something I know. I know there are 5,280 feet in every mile. Cool. Do I know how many hours are in a second? Well, funny enough, I did hours and seconds earlier. I know that in 1 hour, there are 60 times 60, or 3,600 seconds. I just boot someone. I think I might just... Oh, no, I didn't boot you, Heidi. Good. Okay, that's when I booted you for a second. So I have these two conversions that, lucky for me, get me where I want to go. At this point in the game, technically, the organization is relevant. So I can do 5,280 feet in 1 mile. Doing this, I cancel mile, pow, bang, and I get feet in my numerator, which is exactly what I want. And then I do another times bar, another unit conversion, with 1 hour equals 3,600 seconds, or 60 times 60 seconds. And then in this, I blow up my hour, kaboom, kabow, bang, pow, and I end up with seconds, yay, in my denominator. Fantastic. My numerator and my denominators match out. Now all I have to do is the math. At this point, this is why I was saying, going over something where you multiply and divide, you got a few options here. the easiest way to remember, the easiest way to solve this is, of course, to write it out completely. I responded to a message real quick. The easiest way, of course, would be to write this out completely, multiply straight across, which is what corporate overlords at Pearson's did here. Cool. The shorthand approach to solving this issue is to essentially read it from top to bottom. When every time you go, where you zigzag across the question, multiply and dividing. What do I mean by that? What I mean by that is we start with the top left. We start here. We say, okay, I'm going to divide this number. I'm going to divide this number by this number. 200 divided by 1. Okay, that's 200. Then I'm going to zigzag over. I'm going to multiply over 200 times 5,280. All right, that's something I can figure out. Then I divide by 1. Don't need to worry about that. Then I multiply by 1. Don't need to worry about that. Then I divide by 3,600. Okay. So my answer is 200 times 5280 divided by 3,600. So PEMDAS, multiplication division, all at the same level. You just go left to right. That is the calculation you would do. That is the same calculation they do down here, just they stack everything and multiply straight across first. Either way it works. The better you get at this, the more you're going to do this approach here. You're going to learn how to read these calculations. And you're going to figure out you don't have to always stack it in these big, long, fat fractions. Cool. Cars traveling 293 feet per second. Temperature. This one breaks the scale a little bit because the temperature equation, converting temperature from Fahrenheit to Celsius, is an actual equation, not a unit conversion necessarily. It is a unit conversion, but it's a unit conversion that doesn't follow the same steps we've been having. The metric system, temperature is measured on the Celsius scale. Water boils at 100 and freezes at 0. In the Fahrenheit system, which is what we in America use, and it's used a couple other places as well, water boils at 212 and freezes at 32. Fahrenheit, I believe, is actually based on a mercury thermometer, whereas Celsius is based on what water does. Again, Celsius used throughout the world more often makes more sense because the practical version of Fahrenheit is essentially lost to us. It's, again, movement of milligrams of mercury per millimeter. But they still both work. Here is the equations. These are things, honestly, just write them down, punch numbers in. We've talked about variables already. They are easy enough to follow. If you got a number of in Celsius, follow PEMDAS, multiply that number by 1.8 and add 32 to get the Fahrenheit. Right? What is 105 degrees Celsius in Fahrenheit? Fahrenheit, 105 times 1.8, 189 plus 32. 105 degrees Fahrenheit is 221 degrees Celsius. That makes sense because water boils at 100 or 212, so both these numbers should be greater than the boiling point of water. Hey, look at that. Go team, right? Convert the other way. This gross nastiness here. Another way you're going to see this is Fahrenheit minus 160 times 5/9. Either way, it's supposed to be an X there, sorry. Either way, it's the same thing. And it gets you what you need to go. Again, my suggestion, just write these equations down, have them easily bookmarked for the questions. And all it is plugging in the numbers and running through what we're doing here. Oops. There we go. Convert Celsius to convert Fahrenheit to Celsius, plug in the number for the variable, right? I keep saying this stuff is math we already know. I'm just applying a new coat of paint to it. I don't feel as though I need to go over this in depth because we've covered these processes and these steps already. At this point in the game, I'm not asking you to do long division, so life's even easier, right? Just convert it over. Still show me work when you're turning in assignments. What do I consider work? I consider work to be do this and then do this. If you just do those two things, I'll be happy. I want to see the equation built at some point. Don't just give me the answer. Show me at least one step to make me feel like I taught you something. All right, solving applied measurement problems. I might have to blow my nose again soon, just so everyone knows. These are all word problems. I know we hate them. I get it. I'm well aware of that. But it's also what the world actually has, right? Everyone loves Raisin Bran. So, again, if you watch this on YouTube, pause the video after I get done reading. If you are watching this on the live stream, please start working on this as I'm going through the spiel. Cool. A box of Raisin Bran contains 14 ounces of cereal. Okay. Of this, 11 ounces of bran flakes and the rest are raisins. How many grams of raisins are in the box? All right. So, what is the question asking me? The question is asking me how many grams of raisins are in the box. What does the question give me? The question gives me ounces of cereal and ounces of bran flakes. And since I'm such an aficionado with Raisin Bran, trademark, I know that Raisin Bran has 2 scoops of raisins in it from the sun, and it is only bran flakes and raisins. Cool. So what I need to do here is figure out my equation and solve my equation. I don't care about cereal. I don't care about bran flakes. I only care about raisins. So this equation actually starts with subtraction, right? How many ounces of raisins do I have? Once I know how many ounces of raisins I have, then I can do my conversion. I have 14 ounces of cereal, 11 of those are bran flakes. It means I have 3 ounces of raisins to go. Now I need to convert 3 ounces of raisins to grams. That is a imperial to metric conversion, as shown here. So 3 times 28.35 gives me grams of raisins. The math is super simple, right? This is a subtraction followed by a multiplication. 2 separate steps, 2 separate operations. The key is understanding what you need to do and how you do it. Again, Pearson's has this weird blueprint. I never say I would do it if you do know it, it works for you. My suggestion, if you get lost, start writing stuff down, start thinking about it in broad terms. Right? Is that something you guys want me to go over more? I'll take your science as a no. You can, of course, always email me questions as we go forward in the homework. I need to blow my nose again. Excuse me for 1 second. I will leave the example here so you guys can get started on this one before I come back. Hopefully have it all finished. And then we can all have a big party and celebrate how smart we all are. All right. Fantastic. I am back. Hopefully I sound less gross. I feel less gross. All right. The temperature in Cleveland, Ohio is 33 degrees Celsius today. Temperature on this date last year is 94 degrees Fahrenheit. What's the difference in degrees Fahrenheit between the temperature in Cleveland today and the temperature 1 year ago? Fahrenheit to Celsius conversion. Pretty straightforward. Find my equation, plug in my numbers, do some subtraction, 2.6 degrees difference. I'm going to keep stressing this because this is math we've done. This is math that you show that you're capable of doing. You're capable of plugging in a number, filling a variable with a number, and solving the equation. You have PEMDA's operation understood well enough that I don't need to explain to you, hopefully, that you do this multiplication before you do this addition. Likewise, I am of the opinion that you understand how to build and construct the sentence when it's this simple to get the answers required. If you don't know what to do, write stuff down. What is my answer supposed to look like? Well, my answer looks like it's in terms of degrees Fahrenheit between the temperature today and 1 year ago. Cool. So my answer is going to be in some degrees Fahrenheit, right? If you need to go through those steps, I suggest you do them. If you don't need to go through those steps, well, life's easy for you. That is the end of chapter 6. Pretty straightforward chapter. If you're in the live stream, thanks for watching. We will have a couple of things to talk about once I stop recording, so don't leave just yet. If you watch on YouTube, leave any comments down below. I or someone else in the comment section can address them, help you out with this work. And yeah, take care.